Now we come to the concept. One concept that very important in thermodynamics and also very important in physics. It is the concept of entropy. Entropy is a very abstract concept, and in the microscopic level, we define the entropy as the measurement of the disorder of the system. The system that has a lower entropy will have much order than the system that has a higher entropy. For example, if you look at the card in this figure, you can see that this is order in the card, and we can say that this set of the cards has low entropy because it has some order. But if we look at the card here, this is disorder. You cannot see any pattern in this set of cards, and we say that this set of cards has higher entropy. If you study the advanced course in the statistical mechanics, the entropy will be the parameter that join the mechanics of the microscopic system to the thermodynamics of the macroscopic system. However, in thermodynamics, we also have the definition of the entropy, which we will show later that this related to the disorder of the system. The definition of the entropy in thermodynamics. Definition in thermodynamics. Okay, we define that for the system that there is a heat dq enter the system, and we will look at the transfer of the energy dq in the reversible process. And if this process happens when the temperature of the system is T, we define that the change of the entropy of the system is ds equal to the dq over T. You can see that in this definition, we do not define the entropy itself, but it is the change of the entropy. The change of the amount S, which we define as the dq over T, and we call this the entropy. So normally in the calculation of the entropy in thermodynamics, we always calculate the change of the entropy, not the entropy itself. The definition here is in terms of the differential change of the entropy. If we want to calculate the net change of the entropy, we can do that by perform the integration. The change of the entropy from the initial to the final state of the system is equal to the change of the initial state to the final state of the system of the amount of dq over T. Okay, so if during the system, during the process, you know the heat enter in or out of the system, and you know the temperature all the time on that process, you can calculate the net entropy change from this expression. Okay. Now it is interesting to see the change of the entropy of the process that we have discussed so far. First, let's look at the change of the entropy in the Carnot cycle. Okay. In the Carnot cycle, we can see that in the Carnot cycle, we can see that the heat enter the system from the hot reservoir, and the heat enter by the amount of QH is entered the engine, and the engine produce the work W, and the heat go out by the amount of QC to the low temperature reservoir. If you look back to the process in the Carnot cycle, you can see that during the process that the heat enter the system, here we have that in this process, it is the isothermal process which the temperature TH. It means that during the time that the heat QH enter the system, the temperature is a constant which equal to TH. And also, when the heat leaves the system, during the time that the heat QC leaves the system, we have that it is an isothermal process which the temperature of the system is constant Tc. So it means that if we calculate the entropy change of the system in one cycle, the entropy change in one cycle is equal to the entropy change during this process, okay, plus the entropy change during this process. You can see that during the adiabatic expansion or an adiabatic compression, or we can say that in the adiabatic process, we have that Q is equal to 0, which means that dq is also equal to 0, which means that ds is equal to 0 too. But because from the definition, the change of the entropy is equal, ds equal to the dq over t. So if dq is 0, it means that ds is 0. So during the Carnot cycle, we have two adiabatic process and two isothermal process. In the adiabatic process, there is no change in the entropy. In the isothermal process, there is a heat enter or heat leave the system at a constant temperature Th when the heat enter, and at a constant temperature Tc when the heat leaves the system. So there is the entropy change during this isothermal process, and the total change of the entropy is equal to the change of the entropy during this process and during this process. And since the temperature is a constant, we have that the delta S is equal to the QH over TH. This is the entropy change in the isothermal process here. And since here Q is positive, because the heat entered the system, so the change in the entropy is positive. It means that entropy increase. And in this process, the heat leaves the system, right? The heat leaves the system here. So it means that it will decrease the entropy. So we can see that this is equal to QC over TC. So this is the entropy change in one cycle of the Carnot cycle of the Carnot engine. Okay. When the heat enters the system, it increases the entropy. When the heat leaves the system, it decreases the entropy. Now, as we have mentioned that, we can show that the QC over QH is equal to the ratio of the TC over TH. Okay. So, if we put this relation into our expression of the entropy, like we may write out that the QC is equal to QH times TC over TH. And if we put this into this QC, you can see that for the Carnot cycle, in one cycle, we have that the change of the entropy is equal to 0. So it means that in a Carnot cycle, in one cycle, there is no change in the entropy. There is no change in the entropy. This is an example of the cyclic process that all the process in the all process are reversible process. In general, it can be shown that in general, for any cyclic reversible process, as in the Carnot cycle, all processes are reversible, we have that the change of the entropy is equal to 0 in one cycle. It means that if you perform the cyclic process, that all processes are reversible, and you start from some initial state and then go back to the same state, the entropy change will equal to 0. This is the general result from thermodynamics.